Daiki, Matsuoka, Yanaka, and Matsuoka-san now online. So the title is Appositive Projection as Implicit Matrix Extension in Dependent Semantics. Please start.
Okay, can you hear me?
Yes.
Okay, thank you very much. So today I'll talk about our analysis of appositives with dependent type semantics. So let me start with a general observation that natural language can convey secondary content apart from the main point. So here's an example of an appositive relative clause, ARC. So Anne, who is a postdoc researcher, gave a talk at 20. So here, the content of an ARC is not at issue, while that of the matrix clause is at issue. And the difference between the two becomes clearer when you consider the response by the addressee, or here, like, no, she didn't submit a paper. So in this case, this response targets the at issue content, and it is felicitous. However, it is unnatural to respond this way. No, she's still in her PhD course. So this implies that the response by the addressee cannot directly challenge the not at issue content, the content of an ARC. So this type of content has been called conventional implicature in formal semantic literature. Its main characteristic is that it is not at issue, and it typically conveys new information to the discourse. And it leads to an important property of CIs, which is they directly update the common ground, which, in other words, so the hearer cannot respond to or some challenge that. So this leads us to the target of today's talk. So how can we analyze such differences between appositive and at issue content in discourse and inference? All right, so given this motivation, here is the outline of today's talk. So I'll start with some puzzles of scope of interaction and non-interaction between the two types of content. And then I'll introduce our framework, dependent type semantics, DTS, and then I'll describe our proposal, the CI tag. And finally, I'll show you some example analysis to verify our proposal. All right, so the first phenomenon we see is projection. So an ARC is not subject to entailment canceling environments such as negation. So it is not the case that Anne, who danced, met John. So this sentence still implies undanced. And the situation is the same for the conditional antecedent. And so we can technically conclude that appositive content is logically independent of at issue content. So they do not interact with each other. However, there's evidence that shows interaction between the two. Anaphora. So here's an example. John, who nearly killed a woman with his car, visited her in the hospital. So here, the product his inside an LLC refers back to, I need to use the pointer. So his refers back to John in the matrix clause, while the pronoun her in the matrix clause refers to a woman introduced in the LLC. So this means that we cannot just separate these two content because there is kind of cyclic dependency between the two types of content. In other words, these two must be integrated and not separated at the level of semantic representation. And nevertheless, such an anaphora is not entirely free. So here's some examples. So every girl met John who praised her. This is impossible. Or no girl met John who praised her. This is not possible either. The intuitive reason is that there is no specific entity referred to by this pronoun her. In a parallel way, an LLC cannot modify a noun phrase with every or no. So every girl or no girl who danced met John. This type of construction is not possible. So we can conclude that LLCs do not scopeally interact with non-referential quantifiers. All right, so we can see that there is such a complex pattern between interaction and non-interaction. So thus, the specific research question we address is how we can formally account for the extent to which an LLC can scopeally interact with at-issue content. All right, so this is the motivation. And then let's move on to explain the framework, our framework, dependent type semantics. All right. Basically, DTS is based on a type theory called dependent type theory. And the main idea of DTS is that a type represents the meaning of a sentence. And there are two important types. The first is a pi type, which is also called a dependent function type. This is why we use this arrow notation for this type. And it roughly corresponds to universal quantification or conditional inversal logic. And the other one is a sigma type, a dependent product type. So this is a type of pairs. And we use this square bracket notation for this type. And it corresponds to existential quantification or conjunction. And the other thing to mention is that a typing context represents a common ground in DTS. So a typing context is a finite sequence of variable declarations like this. So X1 has type A1 and blah, blah, blah. And we also use this type of notation. So under this typing context and turnstile, M has type B. This is a usual notation in type theory. And I'm thinking about sorry. Maybe. Oh, sorry. Maybe there's a problem with my microphone. Can you hear me now?
Yes, can hear you.
Oh, sorry for that. Okay. Going back to the slides, so we can express the well-formedness of a type inside the theory at the object level. So we can express something like under this typing context, B is well-formed as a type. All right, this is the foundation. And on top of this theory, DTS introduces an underspecified type or an aspirant type. So we use this type is noted this way with square bracket and an aspirant, and it represents anaphoric meaning. And the idea is that this X is a placeholder for a concrete term of type A. So here's a very simple example. A girl came, she danced, and the pronoun she refers back to a girl in the first sentence. So first of all, the semantic representation for the first sentence is this. It is a bit complicated, but first of all, we have a sigma type here. So there exists an X such that X is a girl. So there exists a girl. And pi1 u came. Here, pi1 is a function that takes the first element of a pair, which means that pi1 u refers to X here. And this is the representation for the first, and the semantic representation for the second sentence is this. So here, corresponding to the pronoun she, we use an aspirant type, and the placeholder W requires a type, meaning there exists an X such that X is a female. So we need to find some female entity from the preceding context to fill this placeholder. And we can find one in this case easily. So we can use this girl introduced in the first sentence. Of course, we need to use some word knowledge that every girl is female. But apart from that, it is very easy to construct such proof. And we can then remove this aspirant by replacing this W. And we obtain this rewritten type, which doesn't include this aspirant, that's pi1 s. And again, pi1 is a function that takes the first element, so this term refers to X. So this is intuitive, right? Because this she refers to the entity introduced in the first sentence. All right, this is how DTS works, but the next question is, how can we formalize this type of thing? So DTS gives a nice formalism with a mechanism called type checking. And type checking is a process that validates the validity of an utterance, which means that it checks the well-formedness of its semantic representation. And the aspirant resolution, which I just mentioned, is performed during this process. So here's how. So yeah, now I'll describe the inference rule of the aspirant type. So we need to prove that under this typing context, this aspirant type is well-formed as a type. And we have three premises. The first is that A is well-formed. And then we need to construct a term M of type A. This is necessary because we need to, this amounts to finding an antecedent of an anaphora. And the last one is B, where X is replaced with N, is well-formed as a type. All right, these are the premises, but actually we don't need these two because remember that X is just a placeholder. So as long as a concrete term M has been found, we don't need these two contents. So we can just take the third derivation and output it. And now we have this output, and comparing the conclusion, we can see that the type has changed from an aspirant type to an aspirant-free type. So this is how aspirant resolution is executed in DTS. And this type of type checking based formalism enables us to make an important conceptual distinction. So there are two stages when the addressee accepts or rejects an advance in DTS. So first of all, we start with the condition for felicity. So the semantic representation A needs to be a type. It must be well-formed. And then we execute type checking. So which means that we check the felicity, and at the same time, we resolve the aspirant types. And we obtain aspirant-free type A prime, and it is proved that this is well-formed as a type. And so, which means that intuitively, this is A prime makes sense, but it has not been accepted. So it requires the next step, so checking coherence of A prime with a common ground. And if it is coherent, we can add it to gamma, and we obtain an updated context. So we need two stages of validation. All right, let me summarize things about DTS. So first of all, aspirant types represent anaphoric meaning, and DTS distinguishes two stages. The first is that making sense of A, which is executed by type checking, and secondly, accepting A as true, which amounts to adding it to the context. All right, going back to the topic of CIs, we believe that this two-stage distinction should be useful for the analysis because recall that a CI directly updates the common ground before the other sheets respond, which means that the update with a CI should be before this step 2, which means that during this step 1. And this is just what we're going to do in our proposal. Right, so let's move on to our proposal. We propose extending DTS with a new type, which we call a CI type, defined as follows. So here's the inference rule. We use this triangle notation for this type. And this has two premises. First of all, A should be well-formed. And under this context, where gamma is extended with A, B is well-formed. And after these two derivations are after these two premises are derived, we can ignore or we can discard the first one and take only the second and output it. And again, comparing these two conclusions, we can see that in the typing context, the original typing context, gamma, has been extended with A. So the point is that XA in this CI type is added to the typing context during type checking. And we can intuitively account for this proposal in this way. So the extension launched by the CI type is implicit in the sense that the addressee cannot explicitly choose whether to accept or reject it. So let's see a very simple example. So we'd like to check this CI type, and we execute type checking, in which we not only check felicity and resolve anaphora, but also we extend the context. Then after that, we obtain update the context with the appositive content. And then we check the coherence of the at issue content B prime. Then it is added to the context. So this red and blue shows the difference between the appositive content and at issue content. All right, this is our proposal. Then finally, let's see how this works for concrete examples. We'll see 3 examples. The first is projection. So here is a semantic representation for this negated sentence. We can see that this negated content, who danced met John is here. So who danced, the appositive relative clause is put inside this CI type. And besides, we use this pi type to represent negation. So in DTS, not A is defined as if A leads to contradiction. So it's natural to use pi type here. All right, so let's type check it. So we start with this goal, and we need to derive 2 premises. First of all, the antecedent should be well formed, and the conclusion should be well formed. And for the first sub goal, we need to prove these 2 things, which is required by this CI type rule. So the first is that the appositive content is well formed, and then the at-issue content is well formed. And those two can be easily derived. And then we discard the first and take only the second, which is this. And we can see that the context is extended with the appositive content. Then this is propagated, propagated to the second subgoal, and we have this. And then finally, we reconstruct this pi type. What we do is this. So we put this part into the antecedent and this part in the conclusion, and then we obtain this type. So in the final conclusion, we can see that the appositive content has projected out of negation. So this at-issue content means that it is not the case that metro. All right, this is how projection is predicted. And the next example is boundary crossing Anaphora. So here's an example. John, who met a girl, smiled and she danced. Here she refers back to a girl in the ARC. So let's quickly see the semantic representation. So here is this. So who met a girl is here. So there is a girl U, such as John met. And we type check it. And then the appositive content projects out and is now in the context. And let's assume that this at-issue content is also accepted by the WC. So we now have this updated context. And the point is that the second sentence, second utterance, she danced, is type checked under this updated context. So here is the updated context, and we have this semantic representation. We have an aspirant here corresponding to she, so we can resolve it very easily using the girl in this variable b. So we can resolve it like this. But we can see that Anaphora can be resolved with appositive content. All right, the final example is the most complex. So no interaction with every. So we'd like to show that every girl who met John dance is infelicitous. So let's start with the semantic representation. So it's a bit small, but we use a pi type because it is universal quantification. So for all girl, it is a bit informal explanation, but she met John is the appositive content, and she danced is the at-issue content. And to check it, we first need to check that the restricted girl is well formed as a type, which is trivial. And then under this context, we need to check that the nuclear scope is also well formed. And again, this is a CI type, so we have two derivations here. The appositive content is well formed, the at-issue content is well formed, and again, the first derivation is discarded, and we take only the second one. So now we have come to this point. Here, if we try to reconstruct the pi type, it would be something like this. So yeah, we have a girl here, so we put it in this part. We have dance pi on you here, so we put it this here. But it is not desirable. It is undesirable because in this typing context, we have a free variable u, right, which is not bound by u. And this is blocked because this is an ill-formed context in dependent type theory. So it's the implicit of the sentence is predicted because type checking fails due to this ill-formed typing context. And finally, I'll explain a bit about this ill-formedness of a context. So generally speaking, typing contexts are sensitive to order in dependent type theory. So for instance, this type of backward dependency is okay. However, free variable is not allowed. And this type of forward dependence is not also allowed. So more generally, permutation, which is which is admissible in usual propositional logic, is not entirely free in dependent type theory. So we need to posit that B doesn't have X as a free variable inside. And then we can give kind of generalization for the phenomena. So appositive projection is not allowed when it contains a local variable. So here's how. So we have this large pi type, and X is here, and the appositive content depends on X, this X. And in this case, Bx cannot project out. So this is the general pattern of this phenomena, we think. All right, let me conclude. So our proposal was that, our proposal is the CI type, which extends the context during type checking. And this extension is implicit in that there is no room for WC to challenge or respond directly. And we can account for the scope of non-interaction with something like every or no based on the restriction on the permutation rule. And our future work includes of course, comparison with previous studies. In addition, there is a variant of projection phenomena with a shifted perspective, where the appositive content is not attributed to speaker, but rather to some contextually salient attitude holder, which should be interesting. And that's all for me. Thank you.
Any questions?
So thanks for this talk. So I have a question on the difference between CI and presupposition. So do you think you have separate theory for presupposition as well? Or I mean, both presuppositions and CIs projects. I mean, some way they are very similar, but
Yes.
CI, as you know, it's speaker oriented, basically speaker oriented, and so on.
All right, thank you for the question. Although I have no time to explain that, but in DTS, presupposition is accounted for using this aspirant type. So presupposition is resolved by the preceding context using this aspirant type, while a proposal, the CI context, is not resolved, but extend the context in this way. So this is the difference.
I see. So you have different systems for each, like a status. I mean, you have a distinction between presupposition and CIs.
Yes.
So, okay. Sounds good. Okay.
Any other question?
I can see one Zoom participant is raising their hand.
Yes, that's me, Rusanka.
Yes.
So a brief question, hopefully. So what proof system do you use for the derivations and for the resolution, for the type checking?
Basically, we use Martin Leff's dependent type theory, MLTT, as basics, but we extend it with these two types. These two inference rules, that for the aspirant type and the CI type.
Okay, good. But
Thank you.
also some
Okay.
automatical system, do you use it, or it's still on the stage of the hand work?
Sorry, state of the what?
Is just the theoretical, this is a theoretical system, or do you use some automatic or semi-automatic proof system in type checking?
The answer is more the former. It is still in development, so it is kind of highly theoretical, but there have been some trials to formalize it in Koch and Haskell in detailed application.
Okay, good. And there is a new, but I don't want to take more time now. Probably later I'll give some suggestions for another system, Daiki, because Daiki is trying to consolidate, to unify all those available Koch and Haskell, and etc.
Okay.
But it is a very nice proposal. I like it very much. Thank you.
Thank you very much.
Okay, I have one question. So this is related to Sawada-san's question. So
yes,
in detail, the presupposition resolution can fail. That means that type checking can fail. But according to your proposal, the type checking for CI, I mean the context extension in your sense, always succeed. That never fails. It's my understanding. So
As
the-
for this CI type, it never fails. But as for this aspirant type, the type checking might fail because we may not be able to find the concrete type M for type A.
I see, but the content of appositive clause is automatically added to the context, right?
Ah, yes, yes.
That part always succeeds.
Yes, sure, yes.
Okay. But that sounds a bit strange because sometimes the content of appositive clause is just contradict our common ground, common assumptions. So if I say
Yeah.
Matsuoka-san who is dancing, that contradict our assumptions. So what happens in such a case?
Okay, so your point is false appositive, right?
Yes.
Yeah, the empirical status of false appositive is kind of it's kind of shaking, but there's an empirical study that shows false if a sentence contains a false appositive, then the whole sentence is just to be false. So following this study, we how should I put it? So basically, we check the coherence here, right? In step 2. And if it is not coherent, then at this second step, the infelicity, semantic infelicity is predicted. And false appositive is captured here. So in the step 1, we don't care about the coherence of the context. It just extend the context or resolve the aspirant. And in the second step, we check the semantic like coherence or compatibility. So
But
if yes.
How do you define the process for the second step? What does coherence mean?
That is we have not totally done yet. First of all, we need to check that there is no contradiction, and moreover, we might need to check some pragmatic constraint that something like there is no duplication of an utterance or something like that. We have to think about that.
Okay. I see.
Thank you for your talk. Is there a specific reason to use unspecified types rather than unspecified terms? Because I use unspecified terms in this presentation.
I believe that yes. Sorry, I have not mentioned anything about unspecified type terms, but DTS has 2 variants. So for other audience than Kumakura-san. So we have used unspecified types, but another variant uses unspecified terms, and I believe that there is the choice between these two doesn't affect the proposal about CIs. I think they are kind of orthogonal.
Thank you for your explanation.
We have 2 minutes. Yeah, please.
Should I come here?
Yeah.
Okay, it's just a small comment. So you said you extend the type theory with this new approaches, right? So I mean, if just with take for the just your claim as on face value that it means when you extend the type system, you introduce new connective, right? You introduce new inference rules and so forth. And well, I see there's some inference rule, but they have some interesting side conditions like checking felicity and so forth. So it's kind of, as far as the logic is concerned, it's a kind of a strange logic, right? Because it has a very advanced side conditions. And so, you can
sorry. Which side condition did you refer to?
sample check felicity, right? Or or move.
Felicity. So this part.
Yes, for example, right? Resolve a type, check Felice. So is it, I mean, the question, is it a meta-theoretical, I mean, consideration? So you have the type checking rules, then you perform some manipulation regardless what types are there. So, I mean, you can kind of essentially tree manipulation. So what you do, I would say like QR. So you take one part of the derivation, move another part of the derivation, and then you type check finally, see whether they make sense or not, right? But that operation moving from another, it's not operation in the logic, it's operation outside of the logic, right?
Yes, yes.
So it's kind of saying that you add it into the logic is kind of strange to me because it's operation outside of the logic. You simply have a type checks things. I changed this, I mean, in some kind of way, and then you type check already whether it makes sense, whether, I mean, you can type check or not, right? So it's a method.
I'm not quite sure about what you mean by outside the logic, but these inferences themselves are defined inside the theory.
Yes, but I mean, resolve a types is not a theoretical operation, right? It's, I mean, it's a done kind of outside of the logic, right? Well, the inference rule.
We need to admit that, yes.
Very strictly.
I agree with you. But but we believe that it is necessary to capture anaphoric relations or presupposition in a compositional way.
Well, okay, I don't argue with that. Yes, I mean,
thank you for comments.
It's kind of, it's not a meta-theoretical operation, it's not a theoretical operation. So you're claiming you're extending the type system is, I mean, Martin-Löf type system is very odd to me. That's what.
Okay.
You're using the type system, but you're not extending the type system.
Okay, thank you. Thank you very much.
Thank you very much.